All right, so section 4.4 is on coordinates and basis, right? So, I mean, a basis is actually an important concept in vectors, because you can actually see a basis as, you can see a vector space as a house, and you can see a basis basically as the building materials that you use to build the house. And the glue and that puts everything together, you can see as your vector addition and your vector scalar multiplication. So a basis is actually a ground from which you can work to construct your vector space. Right, so V is a vector space, and you're given a set of vectors. And this set of vectors is a finite set of vectors in V. Then we say that S is called a basis for V if both of the following hold. Firstly, S is linearly independent and S spans V. So when I use the analogy of building materials, right? This is where the building material comes in, because if S spans V, it means I can use S to basically create V. What does it mean for S to span V? It means every vector in V can be written as a linear combination of vectors in S. So the vectors in S are basically the building blocks for each vector in V, because I can generate each vector in V by just taking the vectors in S and using scalar multiples of the vectors of S and adding them together, and I'll get V. So you can see S as the building blocks for V. Now, the second property, which is the linearly independent property, why do we need the property of linearly independence? We're not going to discuss that now. We'll discuss it later in the lecture. But that's also important for us to have linear independence. And you guys will see later on in this lesson why the linear independence is important. Okay, so next we've got some examples of standard bases. So in R3, what's the most basic basis that one can think of? It turns out that the standard unit vectors in R3 forms a basis for R3. And why is that? Because the set of standard unit vectors is a linearly independent set. And also any vector in R3, is a linear combination of vectors in the standard set here, right? Okay, so you can express any vector as a linear combination of the standard vectors. So, for example, you can take A, B, C, and you can write that as A times the first standard unit vector, okay, plus B times the second standard unit vector, plus C times the third standard unit vector. Okay, and you can clearly see that ABC is a linear combination of the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. All right, and we can write how do we solve these values K1, K2, and K3? Well, we can use a basic linear system of equations. We can set up a system of equations, and we can place them in a matrix, and the matrix is going to look like that. Because what is it essentially that you want to solve? You want to solve this linear system of equations, right? Okay, the next one is the standard basis for P2. So what is P2 again? It's all it's basically all polynomials of degree at most 2, right? And the standard basis for that is this set of vectors, 1x and x squared. And the 1x and x squared, they are linearly independent, and you can write any polynomial of degree 2 as a linear combination of polynomial p0, which is 1, polynomial p1, which is x, and polynomial p2, which is x squared. Okay, so for example, like I said, you can take a bx plus cx squared, and you can write that as 1 times polynomial 1, which is in this case is 1, plus, okay, b times polynomial 2, which is in this case x, okay, right, plus you can write c, the third part, you can write c times the polynomial x squared. So there I've just demonstrated that I can write the polynomial a plus bx plus cx squared as a linear combination of the vectors in S. Okay, now why, just for interest's sake, why is this set linearly independent? Why is it linearly independent? Well, if you take k1 and you multiply it with a 1, you take this, set up this equation and go and solve for k1, k2, and k3, right? Plus k3 x squared. You set that equal to the 0 vector, and now you go and solve for k1, k2, and k3. If k3 is not 0, right? So if k3 is not 0, right, then you have a polynomial on the left-hand side that has degree at most 2, and on the right-hand side you have 0. And remember, that has to hold for all x. So again, you're going to get a polynomial because you get on the left-hand side a polynomial of degree 2 for all values of x equals 0. It's going to mean that you're going to have infinitely many roots for a degree 2 polynomial. So k3 is immediately going to be 0. The same argument holds for k2. If k2 is not 0, you've got a polynomial on the left of degree 1, and that on the right-hand side you've got the 0 polynomial, and because it's for all x, it means that for any x that I plug in, I need the 0 on the right-hand side to be satisfied, and therefore you got a polynomial that's got infinitely many roots, but it has degree 1. That's impossible. And again, k1 has to be 0 as well. So k2 0 and k1 is 0. So those are linearly independent vectors, and so it's clear that it's a basis. Okay, so right, so you can, as I previously, I haven't stated it, but again, you can generalize that to Rn. You can take the standard unit vectors in Rn. We know what they look like, and you can form a basis for Rn. And you can take the standard polynomials and generate the whole of Pn. So as an example, what would be the standard basis for Pn? All polynomials that have degree at most n. So that's going to be your standard basis, right? So it's x squared, right? So you're going to go on until you get to xn. So that set there is a linearly independent set, and every polynomial of degree at most n can be written as a linear combination of those vectors. So therefore, it is clearly a basis. Right, then moving on, the standard basis for M22, again, M22, all 2x2 matrices. What is the standard basis? It's the set of these vectors there. So it's basically the matrices 2x2 where you just move the 1 into each position, and you make all the others 0. Now it is clear, you can obviously see that you can write any 2x2 matrix as a linear combination of M1, M2, M3, and M4. Okay, so you would set up, in this case, you would set up basically 4 equations with 4 unknowns. My unknowns will be K1, K2, K3, and K4. These will be the unknowns that correspond to the Ks, right? And you will just plug that into a matrix, and you would clearly solve for this vector here. Okay, so it's basically pretty straightforward. All right, and then lastly, you can actually generalize this to MN, right? So what will be the standard basis there? The standard basis, it will work very much like that. The standard basis will be all the matrices that has got a 1 in exactly one of its it has one as exactly 1 as one of its entries, and all the other entries are 0, and you let the 1 run through all your rows and your columns. So that is what MN will look like. Okay. So in the case of as an example, a 2 by 3 matrix, right? So your standard basis will then look like this. So it's a 2 by 3 matrix. So it's going to be that, okay? And you're going to have, I'm not going to run through all of them. That will be your first one. That will be your second one, okay? That'll be your third one. So you let the 1 run through all its possible positions. And there you go, 1, 0, 0, 0, 1, 0, 0. Okay, that will be your standard basis, 0, 0. Now, please remember that you could find many different bases for a vector space, right? You don't only have one. You can find many different bases. So the basis is not a unique concept. You could get many different bases. So this will be the standard basis for M23 as an example. All right, so a vector space that can be spanned by finitely many vectors is said to be finite dimensional. So that is why we are interested in a basis generally, is to find the dimension of the vector space that we're working with. And knowing what the dimension is in mathematics as you go further, that becomes very important. And a vector space that cannot be spanned by finitely many vectors is said to be infinitely dimensional. All right. All right, so let's look at these examples. I want to look at this one first. Rn, we can span with we can form remember we said that this S is all the standard unit vectors. Okay, so that is a vector with n components. Right, this set is a basis for Rn. Okay, so we go on and on and on. Okay, we said that this set is a basis. Okay, and how many vectors are there in S? There are exactly n vectors. There are n vectors. Right, so the cardinality of S is n. So obviously Rn is spanned by finitely many vectors, so it's finite dimensional. All right, what about Pn? Now Pn is the set of all polynomials of degree less than or equal to n. Now again, what's the standard base there? It's the set of these polynomials, right? We can use these polynomials to span any polynomial. right? And all these polynomials they're linearly independent. Okay, so there's my standard basis for Pn, and there are n plus 1 elements. So the cardinality of S is n plus 1. So therefore, Pn is clearly finite dimensional. And what about the next one? What about the next one is Mn, so it's all m by n matrices, the vector space. Is that finite dimensional or not? Okay, so what is the basis for Mn? It's all the m by n matrices where we've got exactly one of the entries is 1 and all the other entries are 0. Okay, so that is what it's going to look like. I'm not going to, right, so I mean that is what it's going to look like. So you go down and you pretty much go through all the entries and all of them are 0. And then the next entry is going to be 0, 1. You're going to make all the others 0. And you're going to pretty much you're going to construct your whole set from matrices that look like this. And again, how many, okay, so that's going to be my base. And then you're going to have your last one, which is going to be in the last row, in the last column. You're going to have your one there. Okay, so this is a basis. Now, what is the cardinality of S? How many matrices are there in the set S? It's a little combinatorial problem. There are actually exactly m times n, and m times n is finite. So Mn is also finite dimensional. All right. So what about this one? What is P infinity? It's a set of all polynomials. Or it's a set of all polynomials, right? So of any possible degree. Now the question is this finite dimensional or infinitely dimensional? Now, if for us to prove it's finite dimensional, we need to show that there exists a basis for P infinity, and this basis must contain a finite number of vectors, and this this set of vectors need to span P infinity, and they need to be linearly independent. Is it possible? Can I find such a finite set S with finitely many vectors that has the property that the set spans the whole space P infinity and it's linearly independent? Can I do it? All right, so I mean, let's suppose there is a finite set of polynomials that I can span, that I can use the span of to determine P infinity. So what it means is every vector in P infinity can be written as a linear combination of a finite number of polynomials. Now, if you take a polynomial of infinite degree, right, it means that you must be able to span it with, you must be able to write it as a linear combination of these vectors here. Right. Now, that surely means that at least one of these polynomials need to be of infinite degree. Because if all of them are of finite degree, I cannot write a polynomial of infinite degree as a linear combination of finite number of polynomials, all of which have a finite degree. I'm never going to be able to span the whole polynomial. So at least one of these polynomials in S has to have infinite degree, right? Now, if all of them have infinite degree, then I'm going to have a problem when I have to span a polynomial of finite degree, because then again, the same thing, I cannot write a polynomial of finite degree as a linear combination of polynomials of infinite degree. So some of these polynomials have to be finite degree and other polynomials have to be infinite degree. All right, so let's write that down. So at least one polynomial in S must have finite degree, because if all of them have infinite degree, you cannot you cannot write a polynomial of finite degree as a linear combination of polynomials of infinite degree. And at least one polynomial must have infinite degree, because if all of them have if all of them have finite degree, then I cannot write a polynomial of infinite degree as a linear combination of polynomials of finite degree. So at least one of them must be infinite and at least another one of them must be finite. Okay, so because some of the polynomials are finite, I'm going to choose a polynomial pi that has finite degree n. And I'm going to choose n such that n is as large as possible. So from all of the polynomials there that have finite degree, choose pi to have the largest degree. Now, what is the problem with that? What is the problem? Where do I get a problem here? Okay, so the problem comes in. So the problem comes in here. So if you take the polynomial f of x equals x to the power of n plus 1. Okay. Now, can you write x n plus 1 as a linear combination of the polynomials in S? Well, the polynomials in S that have infinite degree are not going to help me. So I need to multiply them with zero scalars. The only polynomials that are going to help me to span f of x, or to write f of x as a linear combination of vectors in S, are the ones that have finite degree. Now, if the polynomial in S that have finite degree, if the polynomials that have finite degree in S, if the largest degree that they can have is this value of n, then I'm not going to be able to span that f of x, because that f of x has got degree n plus 1. So it is clear. So it is clear that x n plus 1 can definitely, it cannot be a linear combination of vectors in S. Okay, so it can't be in the span of S. The infinite degree polynomials are not going to help you to get x n plus 1. Only the finite ones, and the finite ones, the largest degree I already have there is n, so I'm not going to get to x n plus 1. So therefore, it's clear that P infinity cannot be spanned by a finite number of vectors, so therefore it is infinitely dimensional. Alright, so therefore P infinity is infinitely dimensional. Now, the other two, they're a little bit more tricky, and the work that will enable one to answer those questions is start in section 4.5. So is this f? What is f again? F is all real valued functions defined from negative infinity to positive infinity. Now, there's a theorem in section 4.5 that states that if you have a finite dimensional vector space V, then any subspace of that finite dimensional vector space is also finite dimensional. Now, the other two, they're a little bit more tricky, and the work that will enable one to answer those questions is start in section 4.5. So is this f? What is f again? f is all real valued functions defined from negative infinity to positive infinity. Now there's a theorem in section 4.5 that states that if you have a finite dimensional vector space V, then any subspace of that finite dimensional vector space is also finite dimensional. Alright, so there we've got the theorem. If V is finite dimensional, then any subspace of V is finite dimensional. Right. So how can I now apply that to show to show the dimension of f minus infinity positive infinity? Well, let's assume that f minus infinity positive infinity is finite dimensional. Right, then what do we know from this theorem? What do we know from this theorem? This theorem then says that any subspace of f minus infinity positive infinity will also be finite dimensional. All right, so there we got. Okay, so let's suppose. All right, so if f minus infinity positive infinity is finite dimensional, then every. All right, suppose f minus infinity positive infinity is finite dimensional, then every subspace of f minus infinity positive infinity is finite dimensional. Now, what I want you to know is, note the following. What do we know about P infinity? What do we know about P infinity? All right, P infinity is a subspace of f minus infinity positive infinity. Why? Because P infinity, every polynomial is a real valued function, okay? And therefore, every element in P infinity is also in f minus infinity positive infinity. So P infinity is a subset of f minus infinity positive infinity. And P infinity is closed under addition, and it's closed under scalar multiplication, because adding two polynomials is a polynomial, and multiplying a polynomial with a scalar is again a polynomial. So P infinity is a subspace. So what does this theorem tell me? It tells me that every subspace of f minus infinity positive infinity is finite dimensional. Right, so therefore, that'll imply that P infinity is finite dimensional. But we just said, I just proved to you, you cannot span P infinity with a finite number of vectors. So P infinity is finite dimensional. This is a contradiction. It is a contradiction. So it's finite dimensional. All right, and that is a contradiction. All right, this is impossible. So this is impossible. This is impossible. So you cannot assume that f minus infinity positive infinity cannot be finite dimensional. So f minus infinity positive infinity is infinitely dimensional. Don't think about that one. That's an exercise. Can I span R infinity with a finite number of vectors? So go and think of whether that's finite dimensional or infinitely dimensional. Okay, so in this example, what they want us to do is we want to answer the following question. Are the following sets bases for their respective spaces? Right, so the first one, is this a base? Is the set of three vectors a base for the space R3? So for us to check whether it's a base, we need to check two things. Firstly, we need to check that the three vectors span the whole space R3, number one, and number two is the vectors in the set, they need to be linearly independent. Okay, so if either one of those two cases fail, we have that the set will not be a base of the space. Okay, so let's check that now. So we check the first problem there. Right, so we can just take S to be the set of those three vectors, which is 1, 2, minus 1, 0, 1, 0, and the last one is minus 1, minus 3, and 1. All right, is that a base for R3? Now, you can quickly look by inspection that you can see that you can actually write the vector minus 1, minus 3, 1. You can write that as negative the vector 1, 2, minus 1 plus the vector 0, sorry, not plus, I'm going to make that a negative, negative 0, 1, 0. Right, so if you can see there, if you add those two vectors up on the right hand side, these two vectors here, you add them up in that way, you get the vector on the left hand side. Now what is the implication of this? Well, we know that if vectors are, if one vector can be written as a scalar, if a vector can be written as a linear combination of the other vectors in the set, it means the set is linearly dependent. And remember what we said. We said that this is true because if you look at this vector here, 1, minus 3, 1, right? And if we add that to the vector 1, 2, minus 1, okay, and we add that to the vector 0, 1, 0, okay, we get the 0 vector. Okay, so that equation, so what am I, what's K1? K1 is 1, K2 is 1, and K3 is 1. So therefore, that equation we talked about, we set the equation we set up in the first part of section 4.3, that has a non-trivial solution. So therefore, these three vectors are these three vectors are linearly dependent. All right. So if you go and you see basically from what we've written up until now, you can clearly see that this equation here has a non-trivial solution. It has a non-trivial solution. It has a non-trivial solution, and the non-trivial solution is K1 is equal to, go back, K1 is equal to 1, K2 is equal to 1, and K3 is equal to 1. So the set S it's linearly dependent. it's linearly dependent, and so S is not, it's not a base. It's not a base. It's not a base for R3 because it doesn't satisfy the linear independence requirement. Alright, next we are asked to establish whether this set here is in fact a basis for P2. So we need to answer two things. Is that a linearly independent set, yes or no? And number two is we need to check that it spans the whole of P2. Alright, so we take S, our set of vectors, and now we first want to check whether it is linearly independent. Okay, so let's K1, K2, and K3 be scalars, such that K1 times the first polynomial plus K2 times the second polynomial plus K3 times the third polynomial is equal to 0. Okay, and again, like I said previously, this has to hold for all x, for all values of x. Okay, because that's how the vector space is defined. My polynomials are the vectors. Alright, so then you gather all your terms, you gather your x terms and your x squared terms. On the left and on the right you still have the zero polynomial. Now again, what happens if this term is, that term is not 0? If that term is not 0, then you've got the polynomial on the left hand side that has degree 2. And that has to be 0. That degree 2 polynomial has to be 0 for all values of x. Now if that's true, if that's the case, you're going to have a polynomial of degree 2 that's got infinitely many roots. Because it doesn't matter what x you plug in there, it has to always be 0 on the right hand side. So that's literally going to, that can't be. A polynomial of degree at most 2 can have at most 2 roots. So therefore, K1, definitely, K1 minus K3 has to be 0. Okay, that has to happen. All right, by the same argument, what happens if this term here is not 0? Well, again, then you're going to have a polynomial on the left-hand side of degree 1, and that polynomial has to be 0 for all values of x. And if it's 0 for all values of x, it means any value of x I plug in, the polynomial is going to be 0. But what's the problem with that? That's going to lead to a polynomial on the left-hand side that's supposed to only have at most 1 root. It's going to have actually infinitely many roots, which is also impossible. So therefore, I mean, immediately, that is going to imply that that minus K1 minus K2 plus K3 is equal to 0. Okay, and again, by the same argument again, what happens if this term is not 0? Then you've got a polynomial on the left-hand side of degree 0, and it's going to be a non-zero polynomial, and on the right-hand side you've got a 0 polynomial. So that's also going to be a problem. So we also need, in that case, we need K1, K plus K2 plus K3 to be equal to 0. Alright, so from there we have that K1 is equal to K3. Substituting that into the second equation, we get that K1 and those two terms will cancel one another out. So you basically left with K2 being equal to 0. And then from the third equation, K2 is 0 and K1 is equal to K3. So that is going to be K1 plus 0 plus K1, which is equal to 0, and that is going to imply that K1 is 0. And so that is going to imply that K1 needs to be equal to K2, needs to be equal to K3. Alright, and that needs to be equal to 0. So basically, the only scalars K1, K2, and K3 that will satisfy this situation, the only scalars that will satisfy it are the values for K1, K2, and K3 needs to be 0. Okay, so basically what's the conclusion of that? We can therefore say that the set S is linearly independent. Alright, so the set is linearly independent. So we can say this implies that S is linearly independent. It's linearly independent. Okay, so we're halfway there. What's the next thing we need to check is we need to check span. We need to check whether S spans P2. Okay, so I'm claiming that the span of S is actually the whole vector space P2. Now, what is the vector space P2 again? It's the space consisting of all polynomials of degree at most 2. How do we add in this space P2? We add it in the normal way, normal polynomial addition. So we add the x terms to the x terms. We add the x squared terms to the x squared terms. And we add the constants to the constants. How do we take scalar multiplication? We multiply the polynomial with a scalar, the normal way. So those are the two operations that we're working with. So now I want to find out whether the span of S is actually equal to P2. Right. Okay, so I first claim that the span of S is contained in P2. How do you show two sets are the same? How do you show two sets are the same? You show the one set is every element of the one set is in the other, and vice versa. Right? This is what I'm doing now. I'm checking that every element in the span of S is also in P2, but it actually is. Why? Because P2 is a vector space, and P2 is closed under addition. Alright, so we take it from here. Okay, now this is easy to show. So we take terms that I'm familiar with. Let's take f of x in the span of S, and we can f of x is what needs to happen for something to be in the span of S. It must be a linear combination of the vectors in S. Alright, so for f of x to be in the span of S, it needs to be a linear combination of the vectors in S. Alright? Alright, now recall that S is that given set there. So now let's form a linear combination. Alright, take the first function, place it there. Okay, that's my first term. Okay, A1. Alright, take my second function, place it there. Okay, that's my second term, and let's take A2 to be right. Alright, place it there. Okay, so there we've got f of x. That's what f of x looks like. Right, for some a0, a1, and a2 in the set of real numbers. All right. Now, let's just verify that it is in fact, this is a function in P2, and this you can easily see. So that you can then basically see that that f of x is equal to. Okay, so that's what f of x is equal to. Now, what is this? What is this whole thing? What is this? That is a what? That's a polynomial of degree at most 2. That's a polynomial of degree at most 2. So where's this polynomial? This polynomial is actually in P2. This polynomial is in P2 because it has degree at most 2. Okay. So is the span of S contained in P2? Yes, it is, because P2 is a vector space, and vector spaces are closed under addition and scalar multiplication. If you add scalar multiples together, the scalar multiples are again going to be in the vector space. If you take a scalar multiple, it's again going to be in the vector space. So adding all of them together is going to again be in the vector space. So the span of a vector set is always going to be contained in the vector space, because the vector space is closed under addition and scalar multiplication. Okay, so now let's carry on. What's the next thing we need to do? We need to make the following claim. I'm claiming that claim 1.2. I'm now claiming that right. So hence the span, and this will always be the case. The span of a given vector set will always be contained in the vector space. All right, so that's not really the main thing to prove. So I'm going to claim in claim 1.2, I'm going to claim that the space is actually contained in the span of S. Okay, so that is a little bit more difficult to show. How do we show this set is contained in that set? By taking an element from this set and showing it lies within that set. Now, what needs to happen? What needs to happen for something to be in this set? What is the rule that determines membership to that set? What is the span of S? It's all linear combinations of vectors in S. So to show that something is in the span of S, I need to show that it's a linear combination of the vectors in S. All right, so what I do is, let's take a point in there, in P2. What needs to happen for something to be in P2? It needs to be a polynomial of degree at most 2. Okay, there is my polynomial of degree at most 2, and that is in P2, right? So now I need to show that this polynomial, it lies in the span of S. It lies in the span of S. In other words, it is a linear combination of the vectors in S. And that is the aim. There we've got our polynomial. All right. Now I want to check whether it is, if it's in the span of S. Okay, now to establish the answer to this question is we take K1, K2, and K3 be scalars, such that the following holds. Now, I don't know if I can find such scalars, but let's say I want to see if there's a solution to the following equation. So we take our function, our polynomial, that's in P2. There is our set S. Take our first polynomial, place it there. Take our second polynomial, place it there. Take our third polynomial, place it there. All right, so place our k's there. Okay, and then we put equality there. Okay, so from there again, you gather all your terms and you follow the same argument. All right, gathering all the terms, we get that whole polynomial on the left-hand side. And on the right-hand side, we've got the zero polynomial. All right, and this has to be true for all x's. So again, the same argument applies. If this thing is not zero, you have a polynomial of degree 2 with infinitely many roots, which is impossible. If this term is not zero, then again you have the same argument, polynomial of degree 1 that's got infinitely many roots. And the last one is, if this thing is not zero, you've got a non-zero polynomial on the left and a zero polynomial on the right, and that's impossible. So therefore, all those terms are all zero. So therefore, we get... All right, so there we get, we can solve for A0 as that, we can solve for K3 as that, and we can solve for K1 as that. All right, so therefore, from A, we can solve for basically for A2 as K1 minus K3. K1 minus K3. And then from this equation here, from this equation, that one there, okay, we can basically say then that K1 minus K3, so basically you do a substitution there, plus K2 is equal to sorry, no, let me rather say this, A plus K1 minus K3 is equal to minus K2, so therefore A1 plus A2 is equal to minus K2, meaning that K2 is minus A1 plus A2. Okay, so far so good. And then from the third one, we can substitute K1, we can substitute A2 plus K3. All right. Plus K2, which we now solved as minus A1 plus A2. Okay, plus K3. And then from there we can then solve for K3 as a half. All right, and you can clearly see that those terms cancel one another out. All right, okay, so what have we got so far? All right, so remember that K1 is A2 plus K3, and so we basically have that we can just do the substitution, and solve for K1. So we've done what? We've solved what scalar K1 needs to look like, what scalar K3 needs to look like, and what scalar K2 needs to look like. So what's the moral of the story here? So can we find scalars K1, K2, and K3 such that our function f of x or a0 plus a1x plus a2x squared, can we find scalars that such that that is a linear combination of the vectors in S? Yes. So the conclusion is, all right, so we can conclude that the function we already chose from P2 is a linear combination of vectors in S. So what is the moral of the story? We can therefore say that P2 is contained in the span of S. Because remember now, I have found a solution. I found a solution for this, I found values for K1, K2, and K3, and it's clearly a valid solution. So I can express any vector as a linear combination, any vector in P2 as a linear combination of vectors in S, and the scalars that I need to achieve that, K1, K2, and K3, are given by these values here. It's minus A1 plus A2, half A0 plus A1, and A2 plus a half A0 plus A1. So it's possible to take any polynomial of degree n most 2 and write it as a linear combination of vectors in S. So to answer the question, is S a base for P2? Right, so it follows that S is a base. It follows that S is in fact, it is a base. It's a base for the space P2. All right, so again, what I said previously, a base you can see, a vector space you can see as a house, and a base you can see basically as the building materials of the house. And the operations which in addition and scalar multiplication you can see as whatever we use to put those materials together to form the house. So in fact a base is sort of like it's a set containing the building blocks of your vector space, because the base you take and you build your vector space using your base. Adding vectors and scalar multiples of vectors, you can construct your whole vector space.